So, obviously, I'm very grateful to the organizers for inviting me to speak here and to all of you for showing up in spite of all this sense of crisis engulfing the globe. So I apologize because I can see at least 20 people in the audience who understand the issues that I'm about to speak about much better than I do. I'm not really keeping track of what's going on. But so in recent years, I've tended to be peddling a lot of nonsense. But my only excuse is that I make no secret of the fact that I'm peddling nonsense. You know? So if you don't like what I have to say, so you should blame the organizers, mostly. In any case, user beware. I prepared this originally as a, this should, oops. This doesn't, sorry? Oh, up and down, I see. No, that doesn't.
Page up or page down.
Oh, page up or page down.
Or do the left-right arrows. It's in landscape mode, so you see it's not doing. Click the mouse.
See, the machine didn't like my nonsense. It's working. Which ones are there?
Page down or right.
Okay. So page up, page down brings it up. Okay, thanks very much. So that's the disclaimer that I really didn't put a proper bibliography at the end, right? I prepared this originally as a colloquium-style talk, just to give you an overview of what's going on, right, before getting into the specific constructions. In the next lectures, I'll try to give a more detailed exposition of the terminology and the technical constructions that go with the overview that I'll give you today. So let me just remind you, although this must be very well known to everyone, in case there are some people who aren't very number theoretic in the audience, what really the motivation is, although Bjorn as well as David have gone through this to some extent. So I'll just say it in my own words. So we'll start with an X, which is a smooth algebraic curve of genus G defined over the rational numbers. I'll stick to the rational numbers today because that's the theory I understand best. Much of this can be generalized. So Nathan Dogra as well as Daniel Hast have developed a lot of machinery that makes this give you a streamlined way of generalizing this. But as I said, I'll stick to curves over Q. So as you know, when you're trying to describe this in concrete terms, we're actually looking at polynomial equations in two variables with rational coefficients. And the genus can be expressed according to the degree, right? Most of the time, as long as it's smooth, via that degree formula, genus formula. And when we're interested in Diophantine geometry, of course, we're interested in the set of rational solutions viewed at from a geometric perspective. Now, many of you will know that there's this kind of trichotomy that genus 0, genus 1, and higher genus are all quite different. And there's this actual geometric properties when you look at this over the complex numbers that Bjorn alluded to that seems to play a role in the arithmetic. It's hard to make it play a direct role, but this kind of geometric classification is always somewhat in our mind as informing and influencing the arithmetic classification in subtle ways, sometimes direct and sometimes subtle ways. Now, so what I'll do, remind you very briefly, is how the problems have been analyzed thus far in these three cases, genus 0, 1, and higher genus, starting with the genus 0 case. So the first thing to remark, which I'm always quite embarrassed to say this, but it's actually true, right? That even after millennia of studying these problems, genus 0 is the only case that's completely understood. The degree 1 and degree 2. Degree 1 is kind of trivial, but the degree 2 case is non-trivial already, and that's the only case that where we completely understand the Diophantine properties and have a satisfactory theory. So how does that go? The main reason, maybe it's not always described in this form, but main reason genus 0 is understood is because we're able to apply techniques of algebraic number theory, that is class field theory, as well as some elementary algebraic geometry in order to understand the equation. The class field theory part roughly can be described by something that people call local to global methods, while the algebraic geometry part is a kind of geometric generation of solution using methods of sweeping lines. So what does this mean? Well, local to global methods refers to this very well-known fact that the rational numbers can be put inside all these completions. the real completion, 2 eddy completion, 691 eddy completion, and so on. Whenever you complete these fields, the field is now much more actually geometric, right? There's a topology and absolute value, and it's complete and so on, that allows us to solve the Diophantine problem over these kind of fields at least much more easily than over the rationals. So that's I just gave you this picture because, as I said, I prepared all of these slides as a colloquium. I just put up this kind of pictorial bouquet of fields just for fun. But the goal, of course, is to start from this bouquet and return to the center in some way, right? So here's a sample of the kind of theorem that you get when you're in genus 0. So if you look at an equation like this, a quadratic equation, remember this is the d equals 2k, so this is genus 0. So a theorem that's sometimes called the Hasse principle says that this has a rational solution if and only if it has a solution in each of those complete fields. Reals 2 adic, 37 adic, 59 adic, and 67 adic. Yeah? So this is if and only if. Of course, only if it's clear, if it has a rational solution, it has a solution in all those fields. But going the other way is a non-trivial fact. And it's actually using Clad's field theory implicitly, at least at some level. So that's a theorem. So of course, and I guess I should, I wrote this, I'll say it again. The existence of solutions in those five fields can be checked very effectively. There's a criterion formula that you can just use to check whether or not there are solutions in that field. So in that sense, existence of a solution is completely deterministic. So there's a very well-known algorithm for figuring this out. And once you know that the solution is guaranteed, once you know one is well, okay, so you apply this criterion. If there is none, then you're done. You don't have anything more to do. But if the existence is guaranteed by this criteria, then you can just find it by an exhaustive search, by trying, for example. There are, I guess, more refined ways to do it as well. But you can certainly list the possible rational solutions by order of numerators and denominators and keep going until you find one. This doesn't tell you when you can stop very easily, but in any case, there is a terminating algorithm to find the solution once it's guaranteed. Right? And once you found one, so this method, a geometric method I referred to earlier, method of sweeping lines, allows you to describe all the others. For example, the very famous case is where x squared plus y squared equals 1, and you start from this point and consider all lines through that point and generate all the other solutions this way. Okay? So this is what happens. This example is a good picture of what happens in genus 0 case. Now, a point that I won't emphasize so much in these lectures, right, but which I think is a very serious point, and one should start thinking about this in more and more systematic ways, is that at some level, what goes on in genus 0 is that somehow we can all understand the way the rational points sit inside the adelic points. It's not strictly true, but one should view it in this way and try to understand this problem. You may know that there's not that much work, even in situations of genus 0 where the Hasse principle that I referred to earlier is understood. There's not that much work in trying to describe how the rational points really sit inside the adelic points. I think we do have the kind of language and technology necessary to understand that problem, and that somehow underlies a lot of these nonabelian Chabauty constructions that I'll describe and others will describe in the subsequent lectures. Now, moving on to genus 1. So here already things are quite hard and not much, and there's much that's unknown. So this is the degree 3 case, and of course, anything can happen. It might be empty, it might be finite, it might be infinite. So, and there's no known criterion, right, at the moment that tells you which case will actually occur. We still don't know algorithmically how to do this. For example, this local to global principle fails. You can write down degree 3 curves with this property that they have points in all completions, but actually have no rational points. There are examples of that sort, and as an algorithmic matter, there's no algorithm that when you give it, a degree 3 curve will tell you whether or not there exists a point. So it's much more difficult already at that level for existence in the genus 0 than the genus 0 case. But furthermore, even when there is a point, compared to the genus 0 case, it's hard to generate solutions using the existing point. So I'm sure essentially everybody knows that nevertheless, when you have a point, you have this advantage that the points actually have the structure of an abelian group. right? So there is this geometric trick or a method this is this usual picture of the chord tangent law. To add 2 points P and Q, you draw that chord through it and look at the other point of intersection R, then reflect it across the x-axis. And that gives it an abelian group law. And you probably also know the theorem of Mordell that tells you that the rational points via this group law form a finitely generated abelian group. Right? So since it's finitely generated, there's this finite abelian group part and this free part. And this R here is called the rank. That torsion part is a very effectively computable abelian group. Again, I won't dwell on this much. It's this Nagel-Lutz theorem, where if a torsion point, even if you a priori allow them to be rational, when you write it in Weierstrass form, they have to be integral, and y square has to divide the discriminant. So this allows you to just try out all possibility and find the torsion subgroup. However, the computation of the rank, right, and a full set of generators for the Mordell-Weil group, for the group of rational points, that's what it's called, right? It's very difficult. And this really is the subject of the conjecture of Birch and Sinnett and Dyer, which, as you know, is a famous open problem. Now, not as a matter of proof, theorem, and proof, very little is known, right? But in the genus 1 case, so there's this curious fact that when you first start learning the theory, it's quite puzzling. I know I was puzzled by this when I was a student, but at that time, I didn't quite have the machinery that you have now, but still it was puzzling. What was puzzling is the fact that even though the Birch-Sinnett conjecture is not known, if you actually, in practice, if you take an elliptic curve, right, and put it into Sage, it will give you the rank essentially right away and give you a generator. Any small coefficient elliptic curve, instantaneously it computes everything for you that I asserted a moment ago is very difficult, right? So this is a bit mysterious when you first learn it. How do these programs work, right? And I'm sure many of you know this better than I do, but still I remind you that in fact the way it works is that the algorithm for computing this actually uses the conjecture. The conjecture gives you an algorithm. I'll say more about this later. And so this is a very striking fact, that you don't need to prove the conjecture to some extent. If you believe it, roughly speaking, if you accept it like a physicist accepts a physical theory, right, and just deduce consequences, this will always work for you. You don't have to worry about proof. So don't worry about proving the BSD. Just use it. So that's one moral of this whole story, right? But as I said, it's a striking fact that the conjecture gives you the algorithm, like a physical theory does. Right. By the way, in case some old-fashioned people older people like me sometimes don't play with computers, so it's fun to keep computing the Mordell-Weil group in this way and see how the heights change as you compute larger and larger powers and so on. Those kind of computations are all fun. But finally, let's move to the case which is the main topic of this workshop, namely the higher genus case. And as Bjorn reminded us, in that case, we know that the set of points is always finite. So how hard it could be? And the answer is that it's very hard. Finite sets are always the most hardest objects in mathematics. Right? So this is one of them. So why is it hard? Well, let's just remind ourselves of the basic example. So here's the very famous one, right? It was very, very hard to list the complete set of rational solutions. We start those equations. It was very easy to write down the trivial solutions, right? But to know that there are no more, it took hundreds and hundreds of years. That's how hard this problem is. Sometimes it's very easy, of course, depending on what the curve is. So here you can easily see that there are no points, and it's easy to cook up also p-adic versions of this, where you use p-adic criteria. So here there are no rational points because there are no real points, and there are p-adic versions of examples like this. But the general problem, for example, even for examples where there isn't an obvious reason for non-existence. For example, if there's already one solution or some collection of solutions, it's very hard to know when it is you have the complete list. So that was the case with Fermat's equation. So for example, here I just wrote one down randomly. So here's a curve, and it obviously has the solution 1,1729. Yeah. Okay, but obviously, it's a joke. But anyways, for this as well, it's very hard to know if there are any other points. And I don't know. I just wrote this down randomly. Maybe Jennifer can figure it out before the end of the lecture. But I certainly don't know if there are many more solutions. Right, so it's a very hard problem, knowing when you have the full list of solutions. So this leads to the formulation of the main problem that I, anyways, have been working on or thinking about in some form or another for decades. We'll call this the effective model problem. Namely, find a terminating algorithm, give a terminating algorithm, which, when presented with a curve of higher genus as an input, will list for you the set of rational solutions. So that's a problem that's still wide open. In the 1980s and up to the 1990s, I think people often thought about this problem in terms of something called the effective model conjecture. You will have heard phrases of this sort here and there, Spiro, Vojta, also the ABC conjecture. All of these surrounded this problem of finding a priori heights on the size of all rational solutions. They said, well, if you're given a curve, you should be able to compute this quantity such that all rational solutions have numerators and denominators bounded by this quantity. So if you're given such a priori bounds, of course, again, we can all try all possibilities, right? If you knew that beforehand. So this was called the effective model conjectures, various proposals for this a priori bound. And again, maybe ABC is still true, I don't know, but we don't know anyways. So in any case, ABC, even if it were true, the Mochizuki's proposal, even as it stands, doesn't give you such an explicit bound. So although it would go in that direction. So all this is very difficult. So large part of what my lecture is about, if I describe this in rather philosophical terms, it's an approach to this effective model problem using the arithmetic geometry of principal bundles, moduli spaces of principal bundles. In particular, it's a non-Archimedean approach as contrasted to the effective model conjecture, which tries to deal with effective a priori Archimedean bounds. Okay, so let me remind you briefly what the arithmetic principle, what do I mean by arithmetic principle. I'll admit right away, this is rather pretentious terminology because these kind of things have been studied by number theorists for many decades. Right? But I'm just casting it in a different light, or at least trying to look at it from a more of a differential geometrist point of view. As I said, I'm just repackaging it in a pretentious way, but I just feel like there's some reason to be pretentious in that way. So I'll try to explain that to you now. So first, let me just say this in very elementary terms. What do I mean by an arithmetic principal bundle? So there are three pieces of data involved, two groups, G, K, R, and a principal bundle P. So what are these? So when I did write notation like that, K will be a field of characteristic 0. We're mostly interested when K is a number field, of course. And GK is the absolute Galois group. So as you know, it's a topological group with open subgroups given by the Galois groups of these absolute Galois groups of finite field extensions. Now R is also a topological group, but I'll call it a group over the field K. When it has a continuous action of the absolute Galois group by group automorphisms. So some of you will know that there's a kind of shift theoretic way of phrasing all this, but I'm just giving a more hands-on approach. That I'll view the group as being defined over K in some sense, when it has this action of the absolute Galois group. And then P, the principal, this was just what I said just now. So an example, this is not the kind of example that we are very interested in right now, but one example might be you just take an algebraic group that's defined over K, like GLN or an abelian variety, then its K bar points will be a group over K in this sense, because it will admit an action of the Galois group, which is continuous if you just put on there the discrete topology. But the examples that are closer to our mind is when you have something like this ZP1. This is the inverse limit of groups P to the nth roots of unity. Yeah? So this will be a topological group with a Galois action. That is, as you know, these are just compatible systems of roots of unity. So this makes it as a group isomorphic to the p-adic integers, but there's a continuous action of the Galois group. So that's a typical example. Now, a principal bundle that P, the third ingredient, is a topological space P with a compatible continuous actions of the absolute Galois group GK as well as the topological group R. So one will view as the left action and the other as a right action. The right action should be simply transitive, whereas the left action can be very complicated. And the compatibility just means this: if you act by the Galois group as acting by an element of the group R, right, then that's the same as first Galois conjugating everything and acting. So these form a category, which I won't spell out right now, but for the moment, let me note that the principal bundle is trivial. This triviality notion is quite important here. That is, it's isomorphic to the trivial principal bundle R exactly when there's a fixed point for the Galois action. Fixed, that is, it's trivial with respect to all the structure exactly when there's a fixed point. Of course, if it's isomorphic to R, then the origin is fixed, right? Because the Galois group is acting by group automorphism, the origin has to be fixed. On the other hand, if there's a fixed point, then the action by R, when you let R act on that fixed point, that will induce an isomorphism between R and the principal bundle P. So here's an example of an arithmetic principal bundle. Right? So you just take any element of your field K, right? That's not 1, for example, right? Then you get a principal ZP1 bundle by considering P power roots of that. So the trivial principal bundle is where X is 1, but all other elements will give you things that admit actions or compatible actions of P power roots of unity. Now, note, so this is just to give you a flavor of why this might be an interesting framework or language to think in. Well, you see that the principal bundle is trivial exactly when X admits a P to the nth root in K for all n. Right? Because remember, to be trivial, it has to have a point that's fixed by the Galois group, which means it has to have a K rational point, which means X has to have a P to the nth roots for all n. So, for example, when K is a field like C, of course, it's always trivial. On the other hand, when it's a field like Q, it's very rarely trivial, you can guess, right? Of course, if X is 1, it's trivial. 1 is always a P power root of 1 for every n, right? On the other hand, the only case where it's trivial is if X is 1 or P is odd and X is minus 1. In all other cases, you can convince yourself very quickly, all other numbers will not have all P to the nth roots of unity rational. So this is a flavor of how Diophantine properties are built into the structure of this principal bundle. So if K is a field like R, that's of course much simpler than Q, but slightly more complicated than C. And if P is odd, then this principal bundle is trivial for all X. On the other hand, if P is even, if P is 2, that is, right, that's even, right? P is 2, then Px is trivial if and only if X is positive. So as I said, somehow Diophantine properties of some sort are built into the structure of these principal bundles. So these are just elementary examples to give you a flavor of that. So let me just also give you a brief description of something that's very well known and not usually regarded as very useful to think about, but I think it is something we should think about. That is, I mentioned earlier that I'm going to study arithmetic principal bundle, but also moduli spaces of them. Study them in families. For that, let me remind you that if you're given an arithmetic principal bundle, a principal bundle over K in the sense just defined, they can be classified by something called a nonabelian cohomology. So Bjorn already used this word in the morning, so I'll use it again. Right? And I hope you don't mind that kind of object too much. So that is to say, if you choose any element of P, right, then you can get from there a function from the Galois group to the group R, to the topological group R. And how does that work? Well, you just act on your given point Z by an element of the Galois group. Then because R acts simply transitively, there's an element that I denoted here by CPG, right, which relates it back to the original Z. So GZ has to be Z times CPG for some element of R. So that's what I'm denoting as the function from GK to R as G varies. So that function satisfies this condition that's sometimes called the cocycle condition. So all continuous functions from the Galois group to R that satisfy this condition are called the one cocycles. I'm denoting it by Z1 of GR. And then, with respect to a suitable equivalence relation, you get this thing called nonabelian cohomology of the Galois group with coefficient in R. And so equivalence relation is just given by trivial cocycles. So there's a way in which you can conjugate cocycles by elements of the group R to get this equivalence classes. And the point, which I'm not going to spell out right now, is that given the principal bundle, you get this function from the group to R, from GK to R, and its equivalence class inside here is independent of your choice of Z. It just depends on the bundle. And a rather easy theorem is that this gives you a bijection between isomorphism classes of principal R bundles over K and this non-abelian cohomology that I just defined, cocycles modulo equivalence relations. And this H1, this non-abelian cohomology, is an example of what I would like to view in a kind of spatial way as a geometric object in its own right. It's a set, of course, right? But it does have a topology even in this setting, and viewing it as a topological space is actually useful and important, useful and interesting. And my main concern in a lot of the theory, non-abelian Chabauty and its application, is to understand the geometry of these kind of spaces, non-abelian cohomology spaces, in various forms. These are ubiquitous in number theory already. It's not just, as I said, I already admitted that I'm going to describe well-known things in a slightly pretentious way. It depends on what R is. For example, one very important, the one important class of examples is what Bjorn already described. There's going to be a unipotent fundamental group of an algebraic curve, and that has a rather complicated R structure. The way the group acts on these fundamental groups, unipotent fundamental groups, is very hard. The way the Galois group acts on it, right? And I'll give you a sense of how you can study such an action. But two more classes of examples are, for example, in the case in the new proof of model conjecture given by Lawrence and Venkatesh, what they're actually, one way of describing what they're doing is they're studying this non-abelian cohomology space where R is the holonomic group of a specific local system on a curve. So that's an example where you might want to study these kind of families. Another example is where R is a reductive group with a trivial K structure. That is, the Galois action is just trivial. In that case, if you write down the definition of this non-abelian cohomology, it just becomes homomorphisms from GK to R modulo conjugation. So in other words, this becomes a moduli space of Galois representations, which I think many of you will have heard are very important central objects in number theory and arithmetic geometry. So these are all examples of the kind of moduli spaces that we just defined. But finally, as far as these generalities are concerned, when K is a field like Q or number of fields, we have all these completions, right? And the completions allow you to describe these injections of subgroups, absolute Galois groups of local fields sitting inside your absolute Galois group of Q. So given a group and a principal bundle over Q, you can just localize it. You just restrict action to get groups and principal bundles over these local fields. So this is the localization map. From principal bundles over Q to principal bundles over local fields. And there's an associated local to global problem. What do I mean? I guess I didn't write this down. What do I mean by, well, maybe I did write this down. Let's check. Oh yeah, I did write it down. So in fact, what is the local to global problem? It means we want to understand the image of this map. Actually, we also want to understand the kernel, but I'm going to focus mostly on the image. The local to global problem here is trying to understand what collection of local principal bundles comes from a global principal bundle. Yeah. And it's not much of an exaggeration to say that, well, okay, I will exaggerate a little bit. Essentially, all the central problems in number theory can be packaged in some form of this sort. And that is understanding the image of this map. Right. So the philosophical principle, which can be made concrete in a lot of situations, is that in fact, but remember, we started out discussing the local to global problem for points. Yeah? When you have a collection of points over local fields, when does it actually come from a global point? So that's a very hard problem, right? But somehow this principal bundle version seems to be easier in a lot of situations. So let me remind you how this goes for the case of elliptic curves. Yeah? Because this already gives you a flavor of why one might look at these things in terms of principal bundles. And as I said, this is very, very well-known stuff, but where you don't really need to think about these things in terms of moduli spaces, but I'm insisting on that anyways. So let's start with an elliptic curve over the rational number. And I think many of you have seen this exact sequence, right? If you take the Q bar rational point of the elliptic curve and consider the P multiplication map for some prime P. Most often P is just 2. That's already very useful for studying. The sequence for 2 is very, very useful. So then, since we're over Q bar, then multiplication by P map is surjective, and the kernel is exactly the P torsion in Q bar. So you get that exact sequence. And the Galois group G acts on it. So these are all, in other words, I mentioned this earlier, all three terms are groups defined over Q in the earlier sense. Then, associated to this exact sequence, when you apply the Galois action, you get this long exact sequence, right? Having taken Galois invariance, this is no longer surjective. Instead, you get the connecting homomorphism to H1. Right? So if we just cut out this portion of it, the connecting homomorphism part, we get this inclusion from the Mordell-Weil group mod P to that cohomology group, right? Which, as I said, is kind of a principal bundle moduli space of a very simple sort. So here, again, I don't think I'm exaggerating. You know? It really is the central problem of the theory of elliptic curve, understanding the image of this map. You know? So this H1, I'll cut it down in a minute, but essentially this H1 you can somehow understand, and you know that there's this image sitting inside there as a subgroup. Right? And we'd like to understand what that image is. And if you understand that image, that gives you essentially a complete computation of the Mordell-Weil group via an elementary procedure that I won't describe. That is, once you can compute a set of generators for this Mordell-Weil group mod P, it actually leads to a set of generators for the Mordell-Weil group itself. So that implication I won't discuss at all. So, but somehow the understanding this finite group mod P completely is the problem here, right? We're trying to use this H1 in order to do that. Now, Bjorn defined in the morning the Selmer group associated to this situation. So this is how you begin the identification of the image, by putting in the natural conditions, right? And the condition that's been studied for many decades are these Selmer conditions. So what that is, these are the H1 classes that locally come from points. So here's the So here's the diagram. So we have, so this is the connecting homomorphism just discussed. There's a version of it over a completion, QV for every V. Right? So you get this commutative diagram, one involving global principal bundle, one involving local ones, and over there global points and local points, you get this diagram. And of course, since we're interested in the subgroup of that H1 given by coming from the points, right? So to come from the global points there, its localization should come from local points. You know? So the Selmer group is just defined to be the global cohomology classes that come from local points everywhere. And why the reason this is a useful definition is because in principle, this image can be computed. The global image is much harder to compute, but the local image is computable, which makes this Selmer group in principle computable. So I keep saying this, but I never actually do computations, so real computations. I always get nervous when I said things like this. So when Bjorn said it in the morning, I felt very relieved that I can say this as well without fear of too many consequences. Yeah, so that's in principle computable. Right. But, again, I'm repeating what Bjorn said, the key point is that this P Selmer group is actually a finite dimensional FP vector space that's effectively computable, and this gives a bound on the Mordell-Weil group, which then can be refined by this P to the n Selmer group, which also Bjorn discussed. That is to say, if you're interested in what part of this actually comes from points, well, this map here is clearly surjective, right? So anything that comes from points here also has to come here, lift to the P to the n Selmer group. Yeah. So you keep increasing P to the n and more refine the potential for a cohomology class to come from points. And the conjecture, the state Shorter-Average part of the BSD conjecture, which in my mind and maybe many people's mind is really the most important part of BSD as far as solving equations is concerned, is that in fact the image of the Mendeleev group inside cohomology is exactly the infinite Selmer group, right? So those classes that lift to the p to the n Selmer groups for all n. Well, we wrote it as an infinite intersection that looks very scary, but in practice, of course, what that means is that it has to be equal for some finite n, because it's a finite dimensional vector space. It has to happen at some level n, right? And now here's the important part in some sense, well, not in some sense, but in every sense, yeah, is that, in fact, so the conjecture says, the BSD conjecture says that this image has to equal to one of these finite level Selmer groups, right, finite level Selmer images. But in fact, there's a conditional algorithm for verifying this. So this is the kind of thing you'll find in Silverman's book or something, so I'm just giving you a very brief description. So this is this idea that all of these things are effectively computable. So you can start with this and keep trying to decrease the possibility for the image of the Mendeleev group by seeing which classes lift mod p to the n for a larger and larger n. So you keep getting a decreasing sequence of subgroups. Meanwhile, you can also compute the image of the boundary under the boundary map of points on the elliptic curve of bounded height less than or equal to n, height less than or equal to n plus 1. So you get a larger and larger subset in this way. Right? But then, these all lie inside, of course, the Mendeleev group mod p, sitting inside here. But these increase. And what BSD says is that at some point, this, you see, will equal this. Right? And once you're at that point, this thing that's in the middle also has to be equal to this, and you know you're done. So that's the idea of the algorithm. Now, but the only problem is that this algorithm is not guaranteed to terminate. It's the BSD that guarantees the termination. So that's the sense in which we're using the algorithm, using the conjecture to run this algorithm. But once it terminates, you don't need the conjecture anymore. You're done anyway. Yeah, because these inclusions are all true. Yeah? So somehow, in practice, if you believe BSD, you can run this anyways. It always stops in practice. Actually, so every single computation that anyone has ever done where they succeeded in making this stop is experimental verification for BSD. Yeah? And it always works. So that's the point of view according to which proving the conjecture isn't that important. You can use it anyways and just compute points all you want. But nevertheless, of course, we'd like to prove it. Right, so that's the elliptic curve case. And so now let me move on to the description of what happens in the nonabelian case. Yeah? So this, the topic of the workshop, nonabelian Chabauty, how does this generalize this picture for elliptic curves to higher genus curves, and maybe even higher dimensional varieties eventually. So maybe I should say, but for me personally, this what's about to come right now, I've always thought of as generalizing this descent algorithm for elliptic curves. That's been the main goal, and it remains the main goal. Right. So to do this, let's just remind ourselves that if you consider this whole sequence of maps on p torsion, p squared torsion, p cubed torsion connected by p power maps, we take the inverse limit and you get the so-called p-adic Tate module. That's a free ZP module of rank 2. So it's a topological group, but in fact it also admits an action of the Galois group. So this as well is one of the topological groups defined over Q. Right? And the previous boundary maps can be packaged into a big boundary map all at once from rational points to H1, the principal moduli space of principal bundles for this p-adic Tate module. But the key observation that allows us to generalize is that this p-adic this p-adic fundamental group, no, I said it wrong. P-adic Tate module of the elliptic curve is in fact a p-adic fundamental group. That's the sequence in which I wanted to say this. That is, this p-adic Tate module can be canonically identified to the pro-p completion of the fundamental group of E. So this is the notation when I write pi1 superscript P of X bar that you can just define it to be that's not the best definition. I'll give you other descriptions during the next lecture. But you can just define it to be the pro-P completion of the topological fundamental group of the variety. Right? Now, and from that point of view, the p-adic Tate module is just the pro-P fundamental group of the elliptic curve. Meanwhile, the map J, so this is maybe the most important part, the map J that goes from a point to this space of principal bundles, what is it? It actually associates to a point simply the pro-P completion of the homotopy classes of paths from the origin to your point X. And this, I guess I didn't write this down, this is a principal bundle for the fundamental group. Why? Any path can be pre-composed with a loop. So that allows us to view this as a principal bundle. And, well, okay, so that's the map. It associates to the point X, the principal bundle of paths. So it says, again, maybe a pretentious slide, but what you might view as the fundamental fact of arithmetic homotopy theory is that if you have a variety defined over Q and you have rational points, if you take these rational points as base points, then in fact all of these objects admit compatible actions of the absolute Galois group. The fundamental group admits an action, so the Galois group acts on the fundamental group by group automorphisms. It also acts on the space of paths in such a way that the action of the fundamental group on the space of paths is compatible with the Galois action. So next lecture I'll remind you very quickly where this action comes from. Yeah. So this is, now at this point it's a well-known fact and maybe you can even view it as elementary, but I think it's still very profound, the fact that this action, that the topological fundamental group completed with rational base point has this additional arithmetic structure. And that's what we've been studying anyways for years and many other people have been studying this. So then the idea of course is that, okay, so this is an example of the triple Galois group, topological group and principal bundle that arose in the general definition. Right? Then with this formalism, it's clear how to generalize the elliptic curve theory to other varieties. Given even a very general variety, you can define a non-abelian analog of this connecting homomorphism from the theory of elliptic curve by simply associating up to a point the homotopy classes of paths from B to X, which is a principal bundle with compatible Galois action for the pro-P fundamental group. And we're viewing how this varies with X. So when you first learn topology, you may learn this fact that the homotopy classes of paths from B to X is non-canonically isomorphic to the fundamental group. If you choose a path, right, then it's isomorphic, but without the choices, they're quite different, just one axis on the other. But that might seem pedantic when you just look at discrete groups in topology, but when you're viewing it with these extra structures, like arithmetic structure, they turn out to genuinely vary and carry information about the points. Maybe I should also, so in other words, you can really study the variation of those homotopy classes of paths with the base point. I should remark, by the way, I noticed Dick, I didn't know you were coming, very nice to see you here. But anyways, Dick Kane, since he's in the audience, I should remark, I think the first person to really emphasize this was Dick in Hodge theory. You know, when you view this, is that a fair statement? So people had studied the Hodge structures on fundamental groups, arithmetic structures on fundamental groups, and so forth. But a lot of people try to prove that such and such things are independent of the base point. So that's one thing people do quite a lot, and that's important for certain purposes. But Dick really emphasized in the case of Hodge theory that in fact the dependence on the base point is very important and interesting to study. And here we're doing the Galois theoretic version of that. And I think that was really an important insight. Now, of course, for local places, local fields, you get the local version of exactly the same things. We're looking at we're restricting the Galois action to the local fields, and so the previous diagram now fits into a picture like this, right? So the localization map at the bottom is just localization of principal bundles. There's the map that associates to a local point a principal bundle with a local Galois action and the corresponding global thing that fits into a commutative diagram. And as in the elliptic curve case, we're somehow really interested, what are we very interested in? The interaction between the image of this thing and the image of the global local points inside this ambient space of local principal bundles. So this is kind of a big, a complicated translation of the local to global problem. And so I'll define this, remind you of this construction next time. Bjorn referred to it. In order to use this efficiently, we have to also replace this pi1, pro p pi1 by this unipotent completion. So that's an algebraic group. So this as well, Hodge theorists as well as many algebraic geometries have used this in complex geometry as well. We're going to use it in this arithmetic setting. You should think of it as vaguely similar to just taking the pro p group and tensoring with qp. If this is zp, for example, this is really tensoring with qp, and turning it into the QP points of an algebraic group. And you do this at every level in the lower central series, but there's a way to universally do this for the whole group. So that's this notion of a unipotent completion. And all the constructions described so far, Galois action, homotopy classes of paths, all carry over into this unipotent completion setting so that we can replace the previous diagram by this one with unipotent completions instead of the pro-p completion. The advantage, and Bjorn already mentioned this fact, is that once you replace it by the unipotent completion, these moduli spaces, which used to be just topological spaces, now they become algebraic varieties. Actually, I said schemes, and I referred to schemes. That's because I think this is mostly a variety, but sometimes it may be a scheme, and I can't really rule that out, because there's a connecting homomorphism that goes into this construction, and it's not completely obvious that it's always a variety. So far, well, I like schemes as well, but besides that, it may not be a variety. So that's so that I call this, I gave this lecture the name Selmer schemes, even though variety has been used very much in the past. But anyways, these are now algebraic schemes, and the localization map is an algebraic scheme, algebraic map, which means this is a map of algebraic varieties. By the way, this thing here, well, once we replace this by a suitable finite product, it's actually an affine variety. It's just affine spaces. Well, again, we have to modify it, but essentially these are affine spaces. So this is a map that in principle can be computed, whereas that inclusion of rational points is very, very hard. So that's the general idea. So we replace the inclusion of global points inside the adelic point by an algebraic map that can be computed. So the key object of study is not the whole thing, of course, right? So this as well, Bjorn mentioned. You put all these conditions, Hodge theoretic condition, and replace this by something that says H1 sub F, right? That you get conditions like unramified at most prime, crystalline P, and so on. So this I'll go over again tomorrow. And once you have this diagram with all the refined conditions, the idea is you try to find a function on this target space that annihilates the image of this algebraic map, which you can try to do since this is an affine variety. Sorry?
I think I missed that. Could you explain again why are you replacing the pro-p completion by the
Because with pro-p completion, this is just a topological space, but with unipotent completion, these moduli spaces are algebraic schemes. Well, you have to prove it, but it's because these are algebraic groups, essentially. Pro-p completion is just a topological group. This is an algebraic group. Sorry?
also view that as like trivial ZP.
Sorry?
I could also view them as ZP group scheme, the pro-p.
Pro-p completion, actually, you are right. It's possible to modify it in such a way to get something like a ZP group scheme, right? But in order to construct it as a ZP group scheme, I think you need to consider this at some point anyways and view it as a model of this. So anyway, so this is the more convenient object that you have to study anyways at some point. Okay. So this localization map is now a map of algebraic schemes. So you can try to find a map on this affine variety that annihilates the image. We'll call it alpha. Then if you pull that back to the local points, then you get a function on the local points that kills the global points. Of course, now I will specialize more. It's hard to study the product over all V, so we actually focus on the prime P, where P is the same as the QP unipotent completion. And once you do that, we can try to compute the image of the zero sets of all the functions obtained in the previous manner projected to the p points, no, to the p part. So that's a subset of the p-adic points now. And so here's what I refer to as the nonabelian effective model conjecture. So there are two parts. One is that when you do this over all algebraic functions alpha, then you should get exactly the rational points. That the subset of the p-adic points cut out by this strategy as you run over all alpha should cut out exactly the rational point. And then secondly, this set should be effectively computable. So there are many ways to explain why you might expect such a thing, and some of the other lecturers understand this better than I do. But in the first lecture, I'll give you my viewpoint on why you might expect this. But anyway, so that's the non-Archimedean effective model conjecture, not height bounds, but simply that this method gives you a terminating algorithm for finding points. So I was going to, maybe a few remarks. As soon as you find one alpha with a non-trivial p component, right, that annihilates the global limit, actually the QP projection, QP part of the zero set is actually finite already. So it's not some horrible looking computation. As soon as you find one function, then you already get finiteness, which allows you to cut down conceptually as well as practically your picture of what's going on. Furthermore, there's a very reliable conjectural mechanism for producing infinitely many algebraically independent alpha. This is this business of Bloch-Kato conjecture or other motivic conjectures. And there's some sense, this is what I'll explain in the fourth lecture. This conjecture that I referred to, the non-Archimedean effective model conjecture, in some sense is essentially implied by Grothendieck section conjecture. So that's what I'll explain later. So what I was going to do was show you, we started a little bit late, right? 5 or 10 minutes late, I forgot.
Maybe 5 minutes.
5 minutes, okay, yeah, so I'll try to finish within 5 minutes. Yeah. So I was going to show you these examples, but I think, Jen, you're going to show lots of examples of the kind of functions that cut out points this way. So what you get is these various iterated integral functions that cut out global points inside p-adic points, but I'll leave that to Jennifer to explain. I was also going to explain some qualitative results as well as I'll skip over all these slides, sorry. And then there's this wonderful result of Jennifer, Nathan, Jan, Stefan, and Stefan Müller and Jan Teutmann that computes all rational points using this method and the split Cartan modular curve of level 13. But that as well, I will skip for now. Maybe one way of doing this, because see, I wasted too much time with empty philosophizing, so I don't have time for mathematics. But anyways, so since this is all on the web and you're all here, anything on these slides that you'd like to hear more about, we can discuss during the problem sessions. But maybe what I'll do is close with genuine nonsense. Up to here was kind of acceptable nonsense. The last few slides are unacceptable nonsense, but I have to say it anyways. So I've been thinking a lot about the relationship between rational points and critical points. Critical points meaning critical points of functions. Well, what do I mean? Well, you see, I've said that there's this central problem of understanding the local to global principle for principal bundle. That is, images of the localization maps of various sorts on modular space of principal bundles. And I've had this vague analogy between this local to global problem and solving differential equations in differential geometry. That is, in differential geometry, you may be interested in something like spaces of all connections and principal G bundles over a manifold. So that's what this A is, right? And then often you impose differential equations on such connections motivated by physicists like Maxwell's equations or Yang-Mills equations or things of that sort. And then the solution spaces are the classical fields in physics. So I've liked to think about these global principal bundles as being like solutions to equations that define interesting connections among all connections. Now, that sounds very fanciful, and it is. But still, Now, let's remind ourselves that when x is smooth and projective, the rational points are the same as the integral points. Right? So in order to understand the way the integral points sit inside, say, local points, or p-adic points, or a finite collection of v-adic points or adelic points, what we're actually interested in is an intersection. So inside this space of local principal bundle, you have the image of localization, but there are also these extra conditions coming from this p-adic Hodge theory or unramifiedness type of conditions. So that's what I'm writing all at once as H1 sub F. Yeah. So it's actually an intersection. Earlier on, when I put F under the H1 and defined the Selmer scheme, I sort of left out the fact that we were actually taking an intersection. But what I'm claiming is that it's good to think about the intersection structure as being an extra structure. And people in symplectic geometry have done this kind of thing quite a lot. Now here, it's not really exactly the setting of symplectic geometry, although with further work, I think you can turn it into something like that. So I'm going to cheat a little bit and replace U by a somewhat bigger group. So what this is a twisted cotangent bundle of the groups. I take the dual of its Lie algebra and twist the Galois action in the Lie algebra direction by QP1. So that makes sense, and this turns into another group defined over Q. And when you do that, so the point is, in that case, the local moduli space of local principal bundle for this group turns into a symplectic variety over QP. It's an algebraic variety over QP with a symplectic form. And these spaces of interest, those are things that satisfy these local Hodge-Scheredic conditions, as well as the image of the global principal bundles actually become Lagrangian subvarieties. So from this point of view, the space we're actually interested in is a Lagrangian intersection inside a symplectic variety. So I'm not going to explain this at all because I don't really understand. But it's a theorem of many people. I'm just quoting a few people here, but in slightly different setting, that this kind of Lagrangian intersection has a very special structure that's called a -1 symplectic structure. But the key point, whatever that is that this kind of intersection is essentially the critical set of a function. It's Zariski locally the critical set of a function. Now, I can't really describe that function in this setting, but in principle, there's a function whose critical set describes that intersection. And so, if you're interested in global points, so here is this local moduli space that we've kept on using as an ambient space. Inside there, on here, there's a function whose critical set contains the image of the localization map of the for principal bundles. So up to here is a theorem. There's actually a function whose critical set contains this global image. So when you're interested in points, you take that function, you take the differential equation, that is the critical set equation, pull it up there to the v-adic points to get equations that contain the integral points or the rational points, since it's a smooth projective. So this picture is something that I really don't know how to use in a practical way right now. That's the sense in which it's essentially nonsense. But it's really, I can't resist thinking about it. And the reason is explained in this slide. So this is a picture of Fermat. Now, I have the impression that even among mathematicians, it's not always appreciated what a remarkable scientist Fermat was. Right? So he lived in the 17th century, at the time of the scientific revolution, so to speak. And he had 4 important achievements, really foundational achievements in the history of science. So, for example, he, together with Pascal, he founded the modern theory of probability. Can you imagine what an achievement that is? Right? Probability theory, expectation value, computational probability, and so forth. All these things were set out in a letter written by those people. Another achievement was the development of coordinate geometry. We talk about Cartesian coordinate systems, but Fermat actually developed independently of Descartes. Descartes actually didn't like Fermat for a number of reasons, but that was one of them. Another reason that Descartes really persecuted Fermat is because Fermat correctly solved this problem on the slide. Which problem is it? People were interested in explaining the refraction of light. Why is it that light bends when it moves from one medium to another? And Descartes had some very elaborate explanation. I tried to actually read it once. It's very hard to understand what he's getting at. In terms of Well, okay, I can't even say, so forget about that. But anyways, then Fermat gave the correct explanation in terms of the least action principle. What the light is actually doing is minimizing the length of time it takes to get from any point A to any point B. And that explains refraction. So that was so in other words, Fermat was also formulated the first least action principle, which these days underlies all of modern physics, right? Of course, he also founded a lot of the ideas that we do in number theory now, like the study of Diophantine equation, specific study of primes. If you look at the letters that Fermat wrote around that time, he tried to get a lot of the major scientists in Europe interested in number theory. Nobody cared. They thought, well, why are you interested in all these trivial things? You may know that Gauss in the 19th century, for example, poo-pooed Fermat's last theorem. He says, why should anyone care about a problem like that? And I understand in some sense. Number theory often looks quite trivial, right, compared to problems of actual importance in mathematics. Yeah? For me as well, it took quite a while to get attracted to problems like this. You know? Well, anyway, so he had, then eventually you find out that these trivial-looking problems generate all kinds of structures that seem to be almost universal in all over mathematics and its application. So that's kind of a mysterious role of number theory that we still live with. So we want to forget about it, but it keeps coming back to haunt us, right? So Fermat, anyways, had this, although he knew a lot of things and did a lot of important science, he somehow had a concrete intuition for importance of these Diophantine equations, right? Very early on. So, but remember, in this picture here, you find the trajectory of light by solving a differential equation, finding the critical point of a function, the time function, right? And here you're interested in solutions to equations. So it's kind of irresistible to not want to see in some very concrete way, useful way, that these are really two different aspects of the same problem. You know? And here we want to solve the Diophantine equation by finding critical points of a function. Okay, yeah, so I'll stop there and continue with, go back to normal mathematics tomorrow. Yeah, thank you.
Okay, I think in the interest of time, we'll hold questions, and we can find Minhyong, and you can ask him afterwards, and we'll start again in, let's say, about 10 minutes, so just a quick break.
If you ask me questions, I won't have any answers, by the way. Hi, how are you?
Shaky hand.
Yeah, that's right. Do you know the Wuhan handshake?
Brandon,
Do you know?
Brandon, we have a longer coffee break. Yeah, we start at 3:40.